Hello and welcome to the first of a three-part video series taking a look at tropical jets and disturbances. In this first video, we're going to take a look at two jets of the tropics, the tropical easterly jet, which has its origins with the Asian monsoon and associated circulations, as well as the African easterly jet, which has its origins with heating over the Sahara Desert in Africa. And so keep in mind that these are distinctly summertime phenomena. They're driven by diabatic heating in both of these locations, and this diabatic heating is exclusive to the summer. You need the strong, intense sunlight that you see in the summertime in these locations to give rise to these features. But given that we're looking at features that have their origins or greatest impacts over Africa, I thought that a little bit of inspiration would be beneficial for us before we get going into this discussion. So let's load up Totos Africa. I'll leave the rest of the music video to you to find on YouTube or Vivo there, but by and large, we're looking over Africa. I don't know that you necessarily want to dig into the lyrics of Africa to see if there's meteorological connections here. They do talk about the rains down in Africa, which is a little bit important when we get to the discussion on the African easterly jet here. But nevertheless, I hope you enjoyed a few moments there of Totos Africa. So let's dive on into the tropical easterly jet here. So we're taking a look at the solution for asymmetric heating about the equator, looking into the northern hemisphere, and this was our monsoon circulation, looking at the lower troposphere. We had an anticyclone in the southern, the cooler hemisphere in this case, with flow that spiraled out of that anticyclone, crossed the equator, and then emerged and converged into this cyclone within the northern hemisphere. But we know that this heat forcing also increases the thickness relative to locations away from where it occurs. It is relatively warm over the tropospheric column here where we have that heat forcing compared to areas to the north, to the south, to the east, and to the west. And so if we just draw arbitrary thickness contours around this heating, we see that there is a higher height or higher pressure to this surface in the upper troposphere and a lower pressure or lower height relative to this surface here in the lower troposphere. And so if we add in our pressure anomalies, we have our high in the upper troposphere and our low in the lower troposphere. This low is simply the monsoon low that we see depicted in the solution in the upper left. And this high is the strong subtropical anticyclone that is typically found above that monsoon circulation. So for instance, the summertime over Asia and into India, the Tibetan Plateau region in particular, is characterized by a very strong upper tropospheric anticyclone. So if we step forward from here, we get the tropical easterly jet out of this subtropical anticyclone circulation. We have our anticyclone atop the monsoon low here. We have the westerlies at low levels. That's this part of the wind field coming in here just north of the equator. But here at upper levels, we would expect there to be clockwise flow around this area of high pressure. And so equatorward of that, we would expect to see easterly flow. And that's what this E here is depicting, that easterly flow. And the tropical easterly jet is just that. It's that easterly flow on the equatorward side of the subtropical anticyclone that owes its existence to diabatic heating associated with the Asian monsoon circulation. So if we step forward, we can take a look at a broader schematic of features of the Indian Ocean from Africa over toward Asia. We have these black arrows that are depicted here over the Indian Ocean that give rise to the lower tropospheric monsoon circulation, with southeasterly trade winds that then curve and become southwesterly and converge over India and toward the Tibetan Plateau in our monsoon circulation. We have in the upper troposphere, not depicted, is our anticyclone here. here, and we can see the subtropical jet is a westerly jet to the north of that, and the tropical easterly jet is an easterly jet to the south of that. So we have anticyclonically or clockwise turning flow in the upper troposphere here in this case. Our tropical easterly jet extends from the eastern Indian Ocean, where we see this orange arrow originating, over toward Western Africa. And we can see that a little bit better here in the color shading with the image here at right, where anything in the dark blue and above is 20 meters per second and higher, averaged over the summer at 200 hectopascals, so in the upper troposphere. So we have a broad area of 20 meter per second or higher winds extending from the western maritime continent westward toward Eastern Africa here, with weaker winds extending all the way to Western Africa and then back across much of the maritime continent here. The jet is centered around 10 degrees north. Further to the east, it's a little bit closer to the equator. Further to the west, it's closer to 10 to 15 degrees north. And it's centered here at 200 hectopascals. Keep in mind that we're looking at a very warm region of the globe, and so the tropopause is found at a very high altitude, on the order of 100 to 200 hectopascals in this region during the summertime. And it's at that height at which the tropical easterly jet has its maximum intensity. As we might expect, when the monsoon is strong, the low-level westerly flow converging into the monsoon, as well as the upper-level easterly flow diverging away from the monsoon, are relatively strong as well. But if the heating that gives rise to the monsoon is relatively weak, like we might expect to see during an inactive phase of the MJO, so too would the monsoon be weak, and thus the circulations associated with it, including the tropical easterly jet, would be relatively weak. Just like with mid-latitude jet streams, which is a topic that those of you who are seniors and grad students have probably covered, but those of you who are juniors probably have not covered as of yet, there are favored regions for deep moist convection in association with this jet. So we have an easterly jet here, and we have the exit part, which is the end of the jet, and we have the entrance part, which is the beginning of the jet. And then we have the opposite sides. This is the right side of the jet because it's going from right to left. So if you have your back here to the jet, then to the right of you is the right side, and to the left of you is the left side. And so the right entrance region and the left exit region, where the wind begins to accelerate the most for the entrance and decelerates the most for the exit, are regions in which rising motion over a deep tropospheric column are favored. And coincidentally, these happen to coincide with the monsoon region where you see the greatest monsoon rainfall, as well as a region here in Eastern Africa near the Ethiopian highlands where African easterly waves often originate. And so these are distinct forcings that help to maintain the monsoon and help to initiate African easterly waves, which we'll talk about in our next video in this series. So that's it for the tropical easterly jet, but now we want to move on to the African easterly jet here. So here at left, we have a map of the 600 hectopascal zonal wind. So the U component, positive values would be toward the east, negative values would be toward the west here during the Northern Hemisphere summer months. And then we have a vertical cross-section along this purple line here at 0 degrees east from the equator all the way up to 30 north in this case, which is here over Northern Africa. I've annotated in this green arrow here to denote the African easterly jet. It's roughly between 10 degrees and 15 degrees north latitude. It's an easterly jet, so these values that are contoured here are negative, given by the dashed contours. And the values that you see here range between 10 and 12 meters per second along that green arrow here. So you're looking at a jet that is weaker than the tropical easterly jet, but is nevertheless a distinct maximum in the 600 or hectopascal or mid-tropospheric wind speed, zonal wind speed, across Africa and extending into the far eastern tropical Atlantic basin. This jet is typically maximized here around 600 hectopascals, and we can see that in the vertical cross-section here at right. The maximum negative value, denoted by the green E that I've annotated here, is located at 600 hectopascals, and in this case about 12 to 13 degrees north latitude. Peak intensities can range a little bit higher, on the order of up to 15 meters per second. We can even see the tropical easterly jet showing up way up here in the top part of this cross-section as well, with negative 13 meters per second here over Western Africa. Beneath the African easterly jet, we have the West Asian monsoon circulation, and as we'll introduce here in just a few moments, the heat low circulation that is in association with that. Just like the Indian monsoon or the Asian monsoon, we have a lower tropospheric cyclonic circulation with low-level westerly flow coming in across the equator off of the Atlantic and into Africa here, and then that spirals into a cyclone here over the Sahara Desert that has the name of a heat low in association with it. So we have low-level westerly winds that give way to upper-level easterly winds in association with the African easterly jet. So we have strong vertical wind shear on the order of about 20 meters per second between the low levels and 600 hectopascals. From those low-level westerlies on the order of 4 to 5 meters per second in the contours that we have depicted down here at bottom, to the 12 to 13 meter per second easterly flow associated with the African easterly jet here at 600 hectopascals. We can see this in terms of planar views as well. Here's a snapshot of 600 hectopascal heights in the black contours, every 10 meters in this case, so not a standard contour interval, as well as the vector wind. And I've added in the green arrow from the previous slides to denote the African easterly jet. We have a broad anticyclone that's centered over northwestern Africa here on the northwest side of the Sahara Desert. And we have broad easterly flow, as we would expect from geostrophic balance, on its equatorward side. And it's the flow between that area of high pressure and the lower heights closer down to the equator that gives rise to that African easterly jet. But ultimately, what gives rise to this anticyclone, and why are heights lower further to the south, near to the equator? And we'll talk about that here in just a moment. At low levels, here at 925 hectopascals, we have our subtropical anticyclone out over the eastern Atlantic Ocean, and we have a weak area of low pressure, low heights here. These contours are also every 10 meters, so we're looking at 770, 780, 790, 800 meters, and the flow comes across the equator, spirals from the west, and then converges into this area of low pressure here around 20 degrees north latitude, or to the north of the African easterly jet axis. And this is directly over the Sahara Desert, and we can infer that between this area of low pressure at 925 hectopascals and this area of high pressure at 600 hectopascals, near and just to the north of that, we have strong heating. And indeed, this desert, the Sahara Desert, heats very, very strongly. And we'll talk about that a little bit more in subsequent videos, but it's that strong heating over the Sahara Desert that helps to give rise to the thickness differences that give rise to an upper-level anticyclone, low-level cyclone, and the westerly and easterly winds, just like we saw for the tropical easterly jet a few slides ago. So I like this map here of Africa because it helps to show the underlying terrain. We have the Sahara here to the north in the tan colors, indicating the desert, the arid deserts of northern Africa here. We have the jet axis that extends from the Indian Ocean across north-central Africa toward the Atlantic Ocean. And just to the south of that, we see this gray to green shading, and this region here is known as the Sahel. The African easterly jet results from differences in heating between the Sahara, where we see very strong sensible heating given by the sun. You have very strong sunlight over a very long period of time during the summer daytime hours. The sand underneath is a very effective absorber and transmitter of heat energy. It takes in a lot of that solar radiation that comes in from the sun, and it transmits it very effectively back to the atmosphere that resides above in the form of surface sensible heating, which then creates buoyancy, positive buoyancy, so air parcels go up, and they go up and up over greater vertical distances as the day goes on. And so you get these very deep, buoyant air parcels, thermals, that birds, were they to be in the Sahara, which they really don't like to be because there's not a lot else there for them, but could soar to very high altitudes. So you get a deep, almost 400 hectopascal layer of heating over the Sahara Desert. Whereas further to the south, over the Sahel, this is still warm, by Wisconsin standards especially, temperatures on the order of the 80s to 90s degrees Fahrenheit, as compared to the Sahara, where you're looking at 110, 120 degrees Fahrenheit on a relative basis, but much moister, with the flow coming off of the Gulf of Guinea and the equatorial Atlantic Ocean and converging toward the heat low over the Sahara. So you get heating here as well, but it's primarily in the form of deep moist convection that I've indicated here with the gray shading. So you get rain-cooled air at low levels beneath that deep moist convection as compared to the heating at those low levels associated with the dry conditions over the Sahara. So you get very hot here to the north and not as hot further to the south, and even a little bit cooler over the Atlantic Ocean itself, but again, still relatively warm in terms of 80s degrees Fahrenheit by Wisconsin standards. And it's this temperature difference between these regions in the north-south direction that gives rise to the African easterly jet. So we can take a look at this schematic here, and we'll look at this in two ways to help us understand how we get the African easterly jet in response to that heating, particularly that over the Sahara Desert. So we have the Sahel here to the left on the diagram, the Sahara in the gray shaded region here in the middle, and we can envision the Mediterranean Sea is on the far east side or the far right side of the diagram. Pressure is our vertical coordinate, so we have the surface, 600 to 700 hectopascals. The tropopause would be up here toward the top of the diagram. And so this gray bubble that we have here to depict the Sahara is really depicting the depth of the heating associated with the solar heating of the sandy soils across that region here. And we know that that heating is going to give rise to greater thickness of the 600 to 1000 millibar pressure layer as compared to regions to the north and to the south. And so I've drawn in what could be perhaps the 700 hectopascal isobar here, and it is elevated somewhat higher than what we would expect to see further to the south over the Sahel and further to the north of the Mediterranean Sea. So relatively high heights, high pressure here over the Sahara at about 600 to 700 hectopascals. We would also expect the surface pressure to be somewhat lower, similar to what we saw with the monsoon, and this is what gives rise to the heat low, driven exclusively by that strong sensible heating of the Sahara Desert. So we have high to the north and high in the middle troposphere and low in the lower troposphere. From this, if we just consider the flow around each one of these features, we would expect clockwise flow around the area of high pressure, which means westerly flow to the north and easterly flow to the south. And that gives rise to our African easterly jet here. Whereas at low levels, with our heat low, we'd expect westerly flow to the south and easterly flow to the north. And this westerly flow is that which is associated with the West African monsoon circulation. And so we can add those annotations in there. This easterly flow around the anticyclone in the middle troposphere that results from the strong heating of the Sahara is what we conceptualize as our African easterly jet. Whereas the West African monsoon is the flow driven by that heating into that area of low pressure near to the surface, with westerly flow there closer to the equator. We can also take a look at this from a different perspective, where again, we're looking at that strong heating over the Sahara. We have higher thickness here over the Sahara as compared to areas further to the south, the equator and the Sahel, as well as further to the north toward the Mediterranean Sea. So we still have our mid-tropospheric anticyclone and our low-level heat low. We know that friction is going to drive the flow at low levels into this heat low. The flow converges into this region of cyclonic rotation, and as it converges at low levels, we know that it's got to go somewhere, and so it goes upward. So we have strong rising motion in this dry environment through the heat low, and at some point, as you get to the middle troposphere, around 600 hectopascals, it stops ascending. It's no longer positively buoyant. And so when it hits up against something that keeps it from rising, it starts to spread out. So in this case, we can conceptualize it spreading out in two directions, one to the south and one to the north, on either side of this ascending branch through the heat low circulation across the Sahara. We know that if an air parcel is moving toward the north, when we considered the subtropical jet, thinking about the conservation of angular momentum, you're going to higher latitude, but you're getting closer to the Earth's axis of rotation. And so in order to conserve absolute angular momentum, your flow must turn to the right, our Coriolis deflection, and accelerate, so you get a westerly jet. And this could be conceptualized as our subtropical jet, albeit at a lower altitude than we might otherwise expect to see. Conversely, if we look at air directed toward the equator, you're going to a lower latitude and you're getting further from the axis of rotation that goes straight up and down through the poles. And so consequently, to conserve absolute angular momentum, the flow must deflect again to the right, but in this case, if it's going to the south, deflecting to the right causes it to turn to an easterly direction. And so we can also think about the African easterly jet as arising from the conservation of absolute angular momentum. Air parcels that are directed toward the equator away from the Sahara, from that strong rising motion within that heat-driven circulation, must deflect to the right in order to conserve absolute angular momentum, and thus gives rise to the African easterly jet. And so summarizing all of this, we've talked about how diabatic heating drives the circulations of the tropics. And the tropical easterly jet and the African easterly jet are no exception. Spatial variations in diabatic heating associated with the monsoon over India and the Tibetan Plateau, where our heating is maximized, give rise to the upper tropospheric tropical easterly jet. Greater thickness over the Tibetan Plateau in India, subtropical anticyclone, and the easterly flow on its south side is what we characterize as the tropical easterly jet. Whereas over Africa, strong heating over the Sahara has the same impact, leads to relatively high heights over the Sahara Desert in the mid-troposphere rather than the upper troposphere, because this heating is driven more by sensible heating than by a combination of sensible heating and latent heating with thunderstorms, as we see with the Asian monsoon. And so equatorward of that anticyclone, we see easterly flow, which is what we characterize as the African easterly jet. So in our next video, we'll take a look at a feature that is symbiotic with the African easterly jet and serves as sort of the inflection point between our discussion of the meteorology of the tropics as well as tropical cyclone meteorology in the form of African easterly waves. Until then, thanks for tuning in.